Hello, my name is Tevin Ramirez. I'm a senior at Arkansas Tech University, where I am receiving my computer engineering degree and a minor in mathematics. Let's talk about DC motors. DC stands for direct current. To start off, a DC motor is basically an electrical device that turns electrical energy into mechanical energy. The motor has numerous wires that are wrapped either parallel or in series around the rotor to rotate and change the magnetic poles of a magnet. Magnetic poles are usually north on one side and south on the opposite. However, with electrical current applied to a magnet, the north and south of the magnet can be manipulated. When the south of a magnet is placed beside the south of another magnet, then the magnet tries to get away from the south pole of the magnet because opposites attract. If a current is applied to a magnet, that magnet will not switch poles. It will always stay the same pole even if it turns to the north side. The magnet turns forever because it cannot find its opposite pole. So in return, we have rotation, and if the current is extremely strong, the magnet can spin extremely fast. This is basically how a DC motor works. Here's my system diagram. On the right, I have the mathematical equations for the armature, the load, and the gain. On the left, here is just a regular general DC motor picture. Here are our general functions for just the DC motor. On the bottom, this is the structure of the control system, just the general structure. This is my particular transfer function. I use particular parameters shown in my MATLAB code that I plugged into this formula. There are three types of DC motor control system designs that I want to talk about today. First, a feed-forward DC motor. This particular design has an input that goes all the way to the output without any feedback. This feedback DC motor design has an input that is dependent on the output. The input feeds all the way to the output, and the output feeds back to the input. LQR DC motor design. This particular design was created for optimal control and cost efficiency. The output feeds back to the input. This is a great design to use. The objective for this particular lecture, I have design requirements: an overshoot less than 5% and 0 steady state error. So I use particular parameters to place within MATLAB so I can get my desired plot. Open loop response is where the input is not manipulated by the output. Step response is the output response to an abrupt change in voltage or change in velocity. This response is a good response because it is smooth and gradual. However, the steady state error is large. Compensator. Compensator is a circuit or device to compensate for an undesired output. In MATLAB, this is how you change C. My compensator value had to be around 12.47 to obtain the desired overshoot. A compensator just makes your step response go to the right response. Mine was particularly leveled out at 0.1. I want that to be at 1. Root locus is a plot representation for determining the poles in the S-plane of a closed-loop system by varying parameters on the system. This is the root locus plot for the parameters stated by the transfer function. My final root locus and step response. This is the final root locus and step response. Also, here's the time response for the PI system. The higher the value for the compensator, the faster the time response. The black line shows the range of the poles to obtain the desired overshoot. The step response with the compensator met the design requirements of an amplitude of 1. as shown in figure 7 on the right. I also have in figure 6 my continuous time zero pole gain model. Out of the 3 designs that I showed today, the best motor control design is the linear quadratic regulator, the LQR design. This design was created for optimal control at minimal cost. It is called the LQR because a set of linear differential equations and a quadratic cost function were both generated to create this design. Thanks so much for watching. Have a good day.